This video discusses how to evaluate the limits using numerical methods. First, we'll do a quick review of limits, and then I'll go to an example for evaluating a limit using the numerical methods. So what we mean by limits? If I have to evaluate limit x approaches to a, let's say from left-hand side, f of x, what's the meaning of this? Well, we can see it in three possible ways. First, x is not equal to a, but x is very, very close to a. X is very close to a. And thirdly, since this is a left-sided limit, we say x is less than a. All right. Similarly, if I need to find the limit x approaches to a from right-hand side f of x, what does that mean? That also means x is not equal to a and x is very, very close to a, and since this is a right-hand limit, we say that x is greater than a. And there's another thing. If the left-hand limit is equal to the right-hand limit, then we say that the limit x approaches to a f of x exists. Let me write it down. If limit x approaches to a from left-hand side f of x is equal to the limit x approaches to a from right-hand side f of x, then we say that limit x approaches to a f of x exists. Let's say that the left-hand limit is equal to the right-hand limit, and each of them is equal to a value k, where k is a real value. Then we can say that limit x approaches to a f of x is also equal to k. All right, so that's the basic idea of limits. Please note that for continuity, the first condition is that the limit should exist, but that alone is not enough. We must also check for a second condition. So the second condition is when you replace the value of x equals a in the given function f of x, that should be equal to k, which is the limit of the function fx evaluated as x approaches to a. If that condition is not satisfied, we say that the function f of x is not continuous within a neighborhood of x equals a. All right, let me write down that also real quick. For the function f of x to be continuous within a neighborhood of x equals a, we need limit x approaches to a f of x to exist, and also it has to be equal to the value of f evaluated at x equals a. Please also note that limit x approaches to a f of x means it exists, and it also means that limit x approaches to a from left-hand side f of x is equal to the limit x approaches to a from right-hand side. Therefore, some textbooks give this same equation in a slightly different way. It should not confuse you. It is exactly the same thing. Just put it in a slightly different way. Those textbooks write this statement this way. Limit x approaches to a from left-hand side f of x equals limit x approaches to a from right-hand side f of x, and that should be equal to f of a. So no matter what format is given, basically it is the same idea. Now if those conditions are met, we say that the function f of x is continuous within a neighborhood of x equals a. All right, let's keep those things in mind and do an example for evaluating limits using the numerical methods. So here's an example. Let's say we need to evaluate limit x approaches to 2. Let's say from right hand side, x cubed minus 8 divided by x squared minus 4. Well, there are more efficient analytical methods available to solve these kinds of problems, which we will see later. Today, we are going to look at the evaluation of limits using the numerical methods. All right. Now, what's the meaning of x approaches to 2 from right hand side? We said in this case, first x is not equal to 2 and x is very close to 2 and x is slightly larger than 2. Larger than 2 because x approaches to 2 from right hand side. Alright, in order to do the numerical methods, we can actually select a numerical value for x which satisfies all of these conditions. However, before doing that, we may try a shortcut as well. Just look at the first two conditions rather than all three conditions. We said x is not equal to 2, but also we said x is very, very close to 2. X is very, very close to 2 also indicates how about trying x equals 2 directly. Well, it may not be the exact correct approach to evaluate a limit because of this very first condition. However, because of the second condition, we may just forget that first condition for a moment and see if x equals 2 would work for this given question. So what I'm going to do is I'm going to directly substitute x equals 2 and see what happens. If I put x equals 2 in this equation, on the numerator I have 2 raised to the third power minus 8, which is equal to 0. In the denominator, I have 2 raised to the second power minus 4, which is also equal to 0. Therefore, we have a situation which is equal to 0 divided by 0 if I replace 2 directly in the given question. 0 divided by 0 is undefined. Therefore, that direct substitution does not work for this question. However, technically for any limit question, even though this not equality always holds true regarding limit problems, we start by replacing that value because of this second property. However, if the direct substitution leads to one of these kinds of undefined forms, then we can go for the alternative methods. There are so many fantastic alternative methods available. Today, we are going to look at one of those methods. This method is the numerical method. One thing good about numerical methods is that the numerical methods will always work. There are some other analytical approaches. Those may not work for some questions. However, the methods we are going to see today are going to work universally for all the limit problems. So what are the other undefined forms apart from 0 divided by 0? Well, there are so many other possible undefined forms. When you directly substitute the given limit in the problem, if it leads to 0 divided by 0 or 0 times infinity, infinity minus infinity, or infinity divided by infinity, or maybe infinity raised to the 0th power, or maybe 0 raised to the 0th power, and so on, they are all undefined forms in mathematics. Then we have to go for some alternative methods. So the alternative methods that we see today are the numerical methods. Let me go ahead and erase this part. Now I'm going to solve this problem using a numerical method. That means basically I need to select a candidate value for x which will satisfy all three conditions given here. So what is a possible value? Well, x cannot be equal to 2, x must be very, very close to 2, and x must be larger than 2. How about trying a value such as x equals 2.0001? Well, you can always do better. Somebody else can try x equals 2.6071. Maybe another person can try x equals 2.10071. Those are even better candidate values for x than the value that I selected. But anyways, I'm going to select x equals 2.30 and 1 and substitute that value in this question. We can use a calculator and see what we get when we replace 2.0001 for x of that given function. On the numerator, I will have 2.0001 cubed minus 8. In the bottom, I will have 2.0001 squared minus 4. All right, directly use a calculator and do this simplification. A quick hint, you may simplify the numerator and denominator separately and divide those two. However, if you would like to do the calculation in one shot, please make sure to use parentheses correctly. Otherwise, you may end up getting an incorrect answer. All right, so if you do that simplification, we have 3.000075. Well, that indicates that if I selected something better than 2.0001, something like maybe x equals 2.10 my answer right here should be even closer to 3. Therefore, we keep the final answer as equal to 3. We will do another example. It's going to be the same function, but this time I'm going to evaluate the left-hand limit. So for this question, I have limit x approaches to 2 from left-hand side, x cubed minus 8 divided by x squared minus 4. Once again, if we revisit the conditions for limit x approaches to 2 from left hand side, we know that x cannot be equal to 2 and x is very, very close to 2, and since x should approach 2 from left hand side, we need to say that x is less than 2. We already tried the direct substitution of 2 in this function in the previous problem. We saw that it's going to lead to 0 divided by 0 situation. Therefore, we need to find a candidate value for x satisfying all three of these conditions. So what's a possible x value? Well, I need that x to be very close to 2 and I need it to be slightly less than 2. So how about x being equal to 1.9999? Well, we can always do better. You may go up to maybe 10 decimal places. That's even closer to 2 and it satisfies all three of these conditions. Anyways, I'm going to stick to this selected value, x equals 1.9999. All right, when I substitute that in this function, I will get 1.9999 raised to the third power minus 8 divided by 1.9999 raised to the second power minus 4. Now, if I simplify this, I get 2.9999. Well, if you didn't get that answer, retry this simplification with your calculator with these parentheses. You should get 2.9999. That means if I do a better substitution for x, such as x equals 1.109, my final answer should be very close to 3, even closer than the answer that I already have. Therefore, we conclude that the limit of this function should be equal to 3. All right. Now, I have another question for you. Based on the two answers that we obtained, can you answer this question? This limit x approaches to 2, x cubed minus 8 over x squared minus 4 exist? Let's say explain. Well, our answer is yes, it does exist. The reason is, because we have limit x approaches to 2 from left hand side, x cubed minus 8 over x squared minus 4 was equal to limit x approaches to 2 from right hand side, x cubed minus 8 over x squared minus 4. They both were equal to 3. Therefore, we say that limit x approaches to 2, x cubed minus 8 over x squared minus 4 exists and it's equal to 3. Now I have another quick question for you. Is this function x cubed minus 8 all divided by x squared minus 4 continuous within a neighborhood of x equals 2? Well, we saw that the limit exists, but does it guarantee the continuity? Nope, because if the function is continuous, of course, yes, the limit should exist. In addition to that, the value of the function evaluated at that specific x value should be equal to the limit. Now, in order to decide whether this function x cubed minus 8 over x squared minus 4 is continuous within a neighborhood of 2, I need to evaluate the value of the function x cubed minus 8 over x squared minus 4 when x is equal to 2. Can we evaluate that value? Well, that value leads to a situation where 0 divided by 0, which is undefined. That means if I look at the graph of this function at x equals 2, there will be a hole, or in other words, there is a discontinuity at x equals 2. Therefore, we say that even though x cubed minus 8 over x squared minus 4 has the limit as x approaches to 2, that function x cubed minus 8 over x squared minus 4 is not continuous within a neighborhood of x equals 2. Well, in case if you wanted to create a problem with this function so that it is still continuous as well within a neighborhood of x equals 2, in that case we will have to define that function using a piecewise component. We can define our f of x to be equal to x cubed minus 8 over x squared minus 4 everywhere except the case where x is equal to 2. Then the other component of that piecewise function should be defined to be equal to 3 when x is equal to 2. Well, if we define a piecewise function that way, that function is going to be continuous. All right, that's it about the numerical evaluation of limits. Thank you so much.